Welcome to Paradise Podcast number 107, and today we're talking about how Mach numbers, angles of attack, and shock waves affect the boundary layer transition point on cascades, so on airfoils in series. So this is kind of a second part to podcast number 106, but not really. It just follows on with the same paper. So podcast number 106 looked at something called temperature-sensitive paint to determine where this boundary layer transition is occurring. Then they also looked into a numerical model, which they validated. Now we're taking that numerical model and we're going to be looking into these different properties. So how the Mach number, for example, affects where the boundary layer will transition over an airfoil. So we're looking at this paper called Boundary Layer Transition Prediction on Planar Turbine Cascade using temperature-sensitive paint and numerical simulation. This is an open access paper which you can find in the link in the description. So you can access it yourself. You can also watch the video on YouTube and or Spotify instead of just listening to it. And let's pick up where we left off from last podcast. So last podcast, we were looking at just the validation of that CFD model. Let's move on to the additional results that they found through the CFD model. So the numerical results, wall shear and intermittency are more accurate methods to determine the transitional location of the boundary layer. The location where the wall shear begins to increase sharply is the beginning of the transition. Intermittency represents the percentage of time turbulence is occurring. When the intermittency is 0, it represents a fully laminar state. And when the intermittency is 1, it represents a fully turbulent state. The intermittency increases from 0, which represents the beginning of the transition. So let's talk about boundary layer transition and how to measure this. So fundamentally, we look at boundary layers from a point of view like this. So this is a picture that I drew with my little tablet, so excuse the drawing if it's not that great. But we effectively have a wall, which is the flat line. I should probably draw it here. It's this line here, this wall. And then above, we have airflow coming along the wall, and this is at u free stream velocity. And when it hits the wall, a boundary layer starts to form. We all know that. And when it first forms, it's probably going to be laminar, and the laminar velocity profile, so in other words, how the speed of the boundary layer changes when you move away from the wall, will look like something on the left. So this laminar part here, just here. So this means that when you go from the surface, the velocity is going to be 0. Then as you go up, it's going to progress fairly, it's not completely linearly, but it is fairly gentle, the slope in terms of how much it's progressing. And then when you get to the free stream velocity, which is characterized by 99% of the free stream velocity, the top of the boundary layer, then it's going to be pretty much as fast as the free stream velocity. However, as you move along and the boundary layer progresses and it becomes more turbulent, the boundary layer profile becomes significantly more aggressive, let's say. So we have the second aspect here, the second picture. So this means that as you go up from the surface of the wall, the boundary layer velocity increases much quicker, and it's much more rapidly in terms of getting to the free stream velocity. So this comes with a few interesting points. The first one is that the shear stress at the surface of the wall will be significantly greater for the turbulent boundary layer compared to the laminar boundary layer. Another important point is that a turbulent boundary layer typically has more energy near the wall because it has a faster velocity, which means that it can resist adverse pressure gradients, which means that it can stay attached to surfaces much better than a laminar boundary layer. So this is generally the difference between a turbulent boundary layer and a laminar boundary layer. So in this particular case, they're discussing two different ways to look at when a boundary layer is transitioning from, or has transitioned from laminar to turbulent. And I should mention that the transition point is not necessarily a fixed point, like it's not necessarily just one point in space where it goes from laminar to turbulent. Often it occurs over a longer period and depends on the boundary layer transition model. So I mentioned in the last podcast, for example, the bypass model, which is when the boundary layer does transition very at like one instant in time or one instant point from laminar to turbulent. But then you can have natural transition or laminar separation bubble transition, which occurs over a much greater distance. It's not like a definite line. So here they're saying that the location where the wall shear begins to increase sharply signifies the beginning of the transition. And this makes sense because coming back to this picture, if the wall shear stress is increasing, this means that the velocity near the wall is increasing, and that's indicative of a more turbulent boundary layer. The second thing they're talking about is intermittency. And this represents the percentage of time turbulence is occurring. So again, this comes back to transition where if you have like 10% of the time the boundary layer has turbulence in there, that's not necessarily a turbulent boundary layer, that just has some turbulence in there, and that's in the transition point. They're saying here when you get to an intermittency of 1, which means that the entire boundary layer is completely turbulent, then they're saying that's a turbulent boundary layer, and that's a very common rule of thumb. So another thing we should mention is different ways of measuring the boundary layer state, so whether it's laminar, transitional, or turbulent. Another way of looking at this is the boundary layer profiles. So as I mentioned, the velocity profiles. So you can calculate either the momentum thickness and divide that compared to the velocity thickness effectively of the boundary layer. So in other words, you can characterize the boundary layer based on velocity and or momentum. Momentum takes into account mass, obviously, and velocity. So you can look at different shape factors, they're called, which is when how sharp these lines are, how sharply velocities and momentums increase as you go away from the boundary layer. This is another way of looking at this, but they're not looking at those shape factor ways. They're looking at intermittency and wall shear stress. So another point we should talk about with intermittency is, if you remember in the last podcast, I was talking about the CFD setup, and they were using the Arand's model, obviously, Arand's approach. And for the turbulence model, they were going to use the SST gamma theta. And I was talking about this a little bit compared to the SST K omega. Now, you probably know that SST K omega is one of my favorite models. The SST gamma theta is also nice, but I haven't had as much success with it. However, with this explanation here, we can understand now why they chose to use the SST gamma theta instead of SST K omega, and that's because of intermittency. So the SST gamma theta actually calculates the intermittency as one of the equations. That's the gamma part. So if you're calculating it with your CFD, you have the actual result for intermittency there, which is very easy to then extract and analyze. So that's a major strength of using the SST gamma theta in this particular case. If you want to look at intermittency, the equation is right there that you're looking at. If you were to take the SST K omega or K epsilon or whatever other equation, whatever other model like RNG, K epsilon, whatever, they don't really have intermittency in there, so you can't really calculate it easily. So that's one benefit that they're using the SST gamma theta. So it makes sense why they use that model instead of any other one. So now that we've talked about boundary layer transitions and intermittency, let's move on to how the Mach number affects the boundary layer state. So in figure 10, let me zoom out a little bit so you can see these figures a bit more. Here we go. So in figure 10, to study the effect of the Mach number on the transitional location of the boundary layer of the blade, numerical calculations were carried out for Mach numbers less than 1 and above 1 by adjusting the outlet static pressure. Figure 10 shows the distribution of the wall shear stress, as well as the intermittency on the suction side of the blade when the Mach number was less than 1. And the transitional location moved forward with increasing Mach numbers. So when we're below sonic velocities, when you increase the velocity, the transition location moves towards the leading edge. In figure 10a, the transition occurred at about 60% of the chord at a Mach number of 0.56. At this velocity, I would expect probably none of the airfoil to be in sonic flow, because this is probably well below the critical Mach number. So the transitional location was significantly moved forward went to 51% of the chord when the Mach number increased to 0.78. So it went from 60% to 51%. So it's much closer to the leading edge when we increased the Mach number by about 50% again. So from 0.56 to 0.78. When we further increase the Mach number to 0.98, the transitional location moves a little bit further. So it's 48% of the chord now. So only a 3% creeping forward for a significantly greater Mach number, 0.78 to 0.98. And 0.98, I expect that there is going to be sonic flow in over the airfoil at some point, because it's very close to sonic to begin with, and these airfoils are very cambered, which means that the critical Mach number is going to be fairly low. I would expect maybe 0.8 perhaps. So furthermore, the wall shear in the laminar and turbulent parts increased with increasing Mach number. The same transitional location and its variation with the Mach number could be obtained from the intermittency distribution shown in figure 10b. So let's discuss these two different figures now. In figure 10a, we have the wall shear stress, and this is a very easy way of determining when transition is starting to occur, because we can see like it's clear as day when we go from low shear stress to high shear stress, which indicates a higher velocity near the boundary layer, which is indicative of a transitional and or turbulent boundary layer. With the intermittency, we also have a very clear point here as well, where interestingly, the intermittency jumps very quickly from 0 to 1, which indicates a fully turbulent boundary layer for all these Mach numbers. Like it occurs over not even 1 or 2% of the chord. It goes from like being almost completely laminar to completely turbulent, which indicates a bypass transition state. So these figures are very easy to see when the transition is occurring and the turbulence is fully formed. So when we were talking about when the Mach number was less than 1, and we found that when we increased the Mach number, the transition point started to creep towards the leading edge. What happens when the Mach number is greater than 1 though? So figure 11 is again the distribution of the wall shear and the intermittency on the suction side of the blade when the Mach number is greater than 1. And the transitional location moved backwards when we increase the Mach number instead. So when we're in supersonic flow now, when we increase the Mach number, the boundary layer transition point actually moves towards the trailing edge. And this is not that uncommon for a trend that occurs in subsonic flow to be the exact opposite of when you go to supersonic flow. So here we know that the boundary layer transition point moves backwards instead of forwards, but also, for example, when you have a converging diverging nozzle. So a converging diverging nozzle, let me get to my drawing pad here perhaps, is when you have something that looks like this. Converges, then diverges, then underneath we come up, it converges, then diverges. So to begin with, we have a certain cross-sectional area, and then it reduces to a much smaller cross-sectional area in the middle, and then as we go along the nozzle, it increases again. So if we have subsonic flow, let's say it's 0.1 for, oh, I know, whatever, it's subsonic to begin with. Then we get towards the smallest, like the neck of the nozzle, the velocity will increase dramatically. Then as you go past, if you design it properly, the nozzle obviously diverges, then Mach number can actually be above 1 now. So as you diverge the nozzle, the Mach number will increase. So if you were to have a completely subsonic flow here, when you go from a large cross-sectional area to a small cross-sectional area, the velocity will increase. Then you go back to a large cross-sectional area, the velocity will decrease. If you have a completely supersonic flow, going from a supersonic flow at the inlet, when you go to the nozzle neck, the velocity will actually decrease, even though the area is decreasing as well. Then when you increase the cross-sectional area, the velocity will go back up. So that's the exact opposite trends going from subsonic to supersonic flows. So it's not uncommon, as I said, to have different trends going from subsonic regimes to supersonic regimes, as we have here. So they say in figure 11a, the transition occurred at about 86% of the chord at a Mach number of 1.1. When we increased the Mach number to 1.2, the transition location moved back by 2% to 88% now. So we've increased the Mach number by quite a bit, 1.1 to 1.2, and the transition location moves back a little bit. As the Mach number increases further to 1.4, the transitional location moves back even more to 94% of the chord. So it's almost at the trailing edge now. So almost the entire airfoil is under laminar flow now. Furthermore, the shear stress in the laminar area remained constant, while the wall shear stress in the turbulent part increased with increasing Mach number. So in other words, it doesn't matter what the Mach number is in the laminar part, the wall shear stress is about the same. But as we go to the turbulent part, the wall shear stress is affected by the Mach number and it increases with increasing Mach number. In figure 10b, this shows the intermittency distribution with different Mach numbers. The variation trend of intermittency was the same as that of the wall shear stress. So in other words, when we have the laminar flow, the intermittency was not affected by the Mach number. As we have the turbulence starting to form, the intermittency was now affected by the Mach number. And so the higher the Mach number, I guess they all really increase at the same kind of rate. So you can't really say that it increased the rate more quickly. but they're all very quick to begin with. So we can recap here saying that when the Mach number is above 1, increasing the Mach number further reduces how much of the airfoil is in turbulent flow. It moves the transition location further back towards the trailing edge. Finally, let's look at the influence of the angle of attack. So this is important because most airfoils do not operate at just one angle of attack, including cascades. So in figure 12, we can see that it shows the distribution of the wall shear. Let me get this in focus a bit more. Shows the distribution of the wall shear and the intermittency on the suction side of the blade under different angles of attack. And the transitional location moves forward with increasing angle of attack. So in other words, the higher you pitch your airfoil, the more of the airfoil will be in a turbulent flow. In figure 12A, the transitional location occurred at 54% of the chord at an angle of attack of -10 degrees. The transitional location will significantly move forward when the angle of attack went to 0 degrees to 51% of the chord. So about half of the airfoil now is laminar, half is turbulent. If you increase the angle of attack even further to 10 degrees, the transitional location moves even closer to the leading edge to 37% of the chord. So only about a third of the airfoil is now laminar, 2/3 is about turbulent. In addition, the shear stress in the laminar area remained constant with changing angle of attack, while the shear stress in the turbulent part decreased slightly with increasing angle of attack. So it seems like the laminar area, no matter what you really do to it, whether that's increasing the Mach number and or angle of attack, the wall shear stress is going to be about the same. So the same transitional location and its variation trend with angle of attack could be obtained from the intermittency distribution as well. So again, the intermittency shows as you increase angle of attack, the more and more of the airfoil is going to be under turbulent flow. The transition point is going to move towards the leading edge more. So let's move to figure 13, where we're looking at the shock wave influence. So as I mentioned earlier, I can zoom in a little bit here actually. As mentioned earlier, that this cascade, it's going to be operating often in the sonic and supersonic regimes. So it's an important thing to understand how the Mach numbers affect the shocks and everything like that. When the Mach number of the flow is greater than 1, strong disturbances often occur in flow, such as sudden compression of supersonic air. At that time, sudden changes in flow parameters often occur, that is, shock waves. Figure 13 shows the Mach number distribution of the flow field. The air flowed into the leading edge, over the leading edge and out over the trailing edge. When the air flowed over the suction surface, it first passed through the expansion wave, which caused the pressure here to drop sharply. Then it passed through the shock wave, that is the compression wave, causing the pressure to increase sharply. Moreover, the wake was formed behind the base pressure of the trailing edge, and interference between the shock and wave could be seen. So you can see all, like in this CFD in figure 13, you can see all these different variations in color. That's the shocks interacting and creating this pattern. And this is not uncommon. You get this when you get shocks not only interacting with each other, but also rebounding off walls. You can get like shock diamonds, for example, happening. So figure 14 now shows the distribution of the wall shear stress on the suction surface, and the wall shear distribution at 50% of the blade height is shown in figure 14, and it also shows that the expansion wave is generated at about 80% of the chord, so 20% from the leading edge, from the trailing edge, 80% from the leading edge. The shear stress dropped sharply at the chord length of 80% to 83%, and the pressure suddenly increased after the shock wave, resulting in a strong reverse pressure gradient that eventually led to laminar boundary layer separation. So the boundary layer was still laminar at this point, and it separated. So the cascade was not operating at 100% efficiency, I guess. Then finally, figure 15 shows this separation. The local streamlines of the suction surface is shown here, and the existence of the separation bubble can be seen. It's quite small, but you can see this recirculation zone. The laminar separation trigger transition occurred at 85% of the chord, and the wall shear increased rapidly at this point. So, in conclusion, we've found that for this paper, these authors have found that the boundary layer transition of the planar cascade moved forward with increasing Mach number and angle of attack, but that's only when the Mach number was below 1. When you get to sonic flow or supersonic flow, the opposite trend occurs for the increasing Mach number. What's more, numerical calculations above in the supersonic flow were carried out, and these results that the boundary layer moved backwards with increasing angle with increasing Mach number were consistent with experimental results. In addition, the generation of shock waves formed a large adverse pressure gradient that led to the onset of transition. So that's interesting. This adverse pressure gradient actually accelerated this transition location. So that's the end of this podcast. Make sure to like, subscribe, and if you want to get better at CFD and theory yourself, such as what we're going through here, check out our courses in the link in the description. And if you are doing experiments, you need to make sure that you need to measure the density of air and then calculate everything else according to that. Otherwise, you're going to get an error of about 2 to 4% in your experimental data. The reason why is because the density of air changes by about this much on a regular day. So if you go into your wind tunnel at 9 a.m. and you start doing experiments, when you come back after lunch, it's going to be about 2 to 4% different. And you can do these calculations if you like yourself. We've got them on our website, so you can just look at these graphs, or you can do the calculations yourself. It's clear as day. And then if you go between days, weeks, months, seasons, these differences in densities do grow to even 15% realistically. So your data has this massive error in it that you are not picking up, and that makes it very difficult to not only trust it but to find trends. What's more, if you're using this data to validate your CFD is going to be wrong as well because you're using different densities, and the reason why is because you don't even know what the density of air was during your experiments. So we make an instrument to get rid of this error. It's called the Atmosphere Hawk. It actually measures the density of air for you, and it logs it for you. So it's really easy to, and you just plug it into your calculations, and everything's nice. So you can find that in the link in the description. And I'll see you in the next podcast. Peace out, amigos.